Actually, this is my first time visiting Singapore, and it's really a great honor to be here. Today, I'll be talking about quantum information processing based on bosonic modes and mainly on our own work. So this is a roadmap for quantum computation, and it has made tremendous progress over the last about over 2 decades. And as we all know, quantum information is very fragile because of the uncontrolled interaction with the environment. And therefore, the ultimate quantum computer calls for operations on the logical qubit, protected by quantum error correction. And one of the key objectives is to realize a logical qubit on a logical memory with a longer lifetime than the best physical qubit, the physical individual. And that's called to beat the break-even point. And then we need to repeat at the logical qubit level what we have achieved at the physical qubit level. So quantum error correction is really crucial for quantum computation. And this is the outline of my talk. And I will first introduce the bosonic quantum error correction and why we want to use bosonic mode for quantum error correction, what is the advantage. And then we'll discuss briefly the physical system, the circuit quantum electrodynamics architecture, and the universal control of the bosonic mode. And after that, I will talk about our major experimental progress along the line. Then I will try to discuss our recent effort to scale up the bosonic system was the distributed quantum computation architecture. And if I have time, I will talk about a little bit of other applications based on bosonic modes, like quantum metrology. And finally, I will wrap up things with a short outlook. And as we know, if you want to do quantum error correction, there are 2 ways to do this. The first one is to integrate many physical qubits together, like the classical codes and the surface code. And for this kind of multi-qubit encoding, it actually is very challenging in the lab. And because it involves many qubits and involves many error channels, you also need non-local and multi-body interaction in order to do the error detection and error correction. Nevertheless, there has been tremendous progress on the surface code. For example, on Google's Willow chip last year, and we have demonstrated the scaling benefits of surface code, and also they beat the break-even point. And the second approach is try to use the intrinsically large qubit space of a single system, for example, a harmonic oscillator or the bosonic mode to do the encoding. And one advantage is in this large qubit space, and there is only one major error channel. So that is basically the excitation loss in this system. Therefore, there is a limited number of error syndromes that we need to monitor. And also because of this single system nature of this approach, and the operations on a harmonic oscillator on the single system is supposed to be much easier. And therefore, this bosonic encoding should be hardware efficient. And we can realize quantum error correction on a single mode, on a single module, and then we can think about the scaling later on for more complicated applications. And actually, it has been a long time for people to consider install quantum information on the harmonic oscillator. Shortly after the discovery of quantum error correction code, for example, in 2001, and we have the GQT code, and named after Gauss-Mike and Presque, and to encode quantum information just on a harmonic oscillator. I think Steve is the one who demonstrated the first GQT code in the superconducting circuit. And in this system, the best physical qubit is defined by the 2 lowest energy levels, level 0 and level 1. And because in this case, the decay rate is the slowest. And this defines also the break-even point of this system. And apparently this system is not correctable. And if you want to do error correction, you need more redundancy. you have to add more or higher energy levels into the system and to get information redundant. But you have to pay a price, and then the decay rate will be faster. And since the decay rate is going to be proportional to the number of excitation. And this is actually the price you have to pay for any quantum error correction code, right? If you want to do the redundancy, you either bring more error channels, or like here, you make the error rate faster. Hopefully, we can use the active quantum error correction operations to overcome this negative effect, and eventually we want to extend lifetime of the stored quantum information. And if you just have a harmonic oscillator, it's a very quantum system, but it's difficult to manipulate, and you need some nonlinearities. And our way is generally to use a very nonlinear system, that's the qubit 2-level system, coupled to the harmonic oscillator to bring the necessary nonlinearity. Then we can have the universal control of harmonic oscillator. And we'll talk about this control later on. And in the superconducting system, basically, we can imagine to have a structure as simple as this. You have a storage cavity, the microwave cavity has very good coherence time, and you store the quantum information in this harmonic oscillator. And then you have a superconducting qubit coupled to this cavity, and this coupling can provide control, detection, and error correction on the stored information. And then, of course, you need a readout cavity to read out this ancillary qubit. That's basically the structure we are working on, and we are following this second approach for quantum error correction. And besides having infinitely large Hilbert space for quantum error correction, the bosonic modes also have other advantages. For example, they can be based on various degrees of freedom, like the energy, frequency, or even the spatial mode. And they can propagate over long distances, like a photon. That's basically the bosonic mode. And they can hybrid with different systems. Therefore, they have a kind of wide applications, not only in computation, but also in simulation, metrology, and communication. And then a few years ago, we wrote a review paper summarizing the applications of the bosonic modes and the bosonic codes in these directions. And I think Yuan here also wrote a very nice review paper on the bosonic qubit in circuit QED. And there are basically two major bosonic modes. And the first one is the electromagnetic modes in the microwave cavity. And we have learned this very well, and we can have a strong coupling between qubit and this mode. And the other type of bosonic mode is the mechanical oscillation mode or phonons. And these phonons can also have good coherence times. But more importantly, because phonon, the propagation speed of phonon is about 5 orders magnitude slower than the speed of light. So at the same frequency, the wavelength of phonon will be 5 order magnitude shorter than the speed than the microwave. And therefore, these phonons at gigahertz, they have a much smaller mode volume. So they are easy to scale out. And actually for these two types of modes, and there have been tremendous experimental progress. Time limitation, I'm not going to go through all these things. In the superconducting circuit, and we basically have these 3 types of bosonic quantum error correction code. And they are the CAD code, binomial code, and the GKP code I mentioned earlier. And here I just draw the Wiegand function of the typical code in the code and the error spaces. And for all these 3 error correction codes, they have been experimentally demonstrated in the lab. And here the binomial code is our work, so I will mainly focus on the binomial code. So the binomial code was discovered by Professor Gerlin and John. It's in the paper 2016. And for the general binomial code, they can exactly correct the photon loss error A and the gain error A dagger and diffusion error N to different orders. And for different error sets, basically you can have the corresponding binomial code. And if we just expand the code basis in the fork space. And you will see this coefficient is just binomially distributed. And that's why this code is called binomial code. And actually, there's a few advantages for the binomial code. And you can check if they are exactly orthogonal to each other. This is a little bit different for the head code. They are not exactly orthogonal. For the binomial code, they can be exactly orthogonal. And they have exact equal mean photon number. And since all these space they are orthogonal, we can have an explicit unitary operation to recover the loss of energy. And this is also a truncated Fock space. And in principle, and we can have a smaller effect, and the manipulation of the code can be easier. So just give you an example. And if you want to have the code and can only tolerate a single photon loss error, that's the A error, and then you can get the lowest order binomial code. The logical 0 is just the superposition of 0 and 4. And the logical 1 is just the Fock state 2. And they are the even parity state, and you can do the parity check to know the error happens or not. And since this code can only tolerate one error, once you detect the error, you have to do the recovery. Otherwise, you're going to lose the information. And if you want to tolerate more errors, and you have to use more redundancy. For example, if you want to tolerate 2 errors, you can use the superposition of 0 and 6, 3 and 9 as the basis. And in this case, you can tolerate 2 photon losses without losing the information. Of course, you can have build many other even higher order binomial code. So that's basically why we want to do quantum error correction, and we will focus on the binomial code in our group. Now, let's try to describe the physical system a bit. I think maybe most of you have already know this well. For this silver conducting qubit coupled to the harmonic oscillator, this system is the so-called circuit quantum electrodynamics. And we use this Hamiltonian to describe this system. And generally, the silver conducting qubit is far detuned from the harmonic oscillator. And we have this dispersive interaction, which is proportional for this interaction. We know the total interaction proportional to the photon number in the cavity. And this is just the harmonic oscillator, and this is the qubit. And because of the dispersive interaction, we have 2 harmonic oscillators here, responding to different state of the qubit. And the energy spacing is different by chi, which is the interaction strength. And on the right, you can see the frequency component for each individual system. The qubit frequency depends on the number of photons or excitation in the cavity. And the cavity frequency, of course, will depend on the state of the qubit. And based on this interaction, we can have a universal control for the system. You have a controlled operation on the other system based on the first one. And for example, we can use the displacement in combination with the selective number-dependent arbitrary phase on the qubit. We have the so-called snap gate to do a unitary operation on the cavity. And another general way is to use the optimal control, and you can fully explore the control parameter space to optimize, to do numerical optimization to get the control pulses. And it's first developed in the AMR system, but I think nowadays in the superconducting system, we use quite a lot for this kind of grip approach. And both of these approaches, they are targeting the closed quantum system. So you get a unitary operation. And recently we just extend this a little bit. And during the numerical optimization, and we can include the system decoherence. So therefore we call this is approximate open graph approach. And this approach can give a much higher yield to generate high quality pulse with higher operation fidelity. And I'm not going to describe this, but if you want to see, you can check this paper. And another thing is for the superconducting community, we benefit a lot from amplifiers, and they are quantum limited, so we can have very high fidelity single shot readout. And people also tried, including ourselves, we developed faster real-time feedback control based on FPGAs, and the latency can be very short. We can do the feedback in about a couple of hundred nanoseconds, much shorter than the coherence time of the system. And based on the high fidelity single shot readout of the qubits, and also this kind of feedback control, and based on theory paper, you should be able to do arbitrary operation, quantum operation on an open system. Actually, for quantum error correction, it's just open system control. By purifying the quantum system, when we try to remove the entanglement between the system and the environment. And based on this approach, and the recent, well, I guess a few years ago, we demonstrated the high efficiency arbitrary quantum operations on a high dimensional quantum system. So the protocol is basically this. And we have a high dimensional system, like a harmonic oscillator. And all we need is just the ancillary, the two-level qubit. So this is the minimum physical resource we have to use. And then we just do a unitary operation for this composite system. And this is a conditional unitary operation. Conditional operation, and depending on all the previous measurement result of this ancillary qubit. And this unitary operation can be realized with a snap gate or grave pulses. And then we just measure this ancillary qubit projectively. And after the measurement, we reset the ancillary to the ground state for the next round operation. And the result, the outcome, will be restored in classical register. And the result will be used for the next round of this conditional unitary control of this system. And only after a few rounds, and then you can have arbitrary quantum operations on this high-dimensional system. And especially we can get the arbitrary POVM measurement on this high-dimensional system. And based on this POVM measurement, we can do the unambiguous discrimination, not only on the quantum state, but also on quantum operations. And this is, again, another recent paper. We use this, in the previous slide, we have the arbitrary POVM measurement, and we can do the unambiguous discrimination of six-fold displacement operators, and also the conclusive probability is very close to the saturated to the theoretical upper bound. And we can also do the discrimination of non-unitary operation. So again, I'm not going to go details to this work. That's basically the universal control. So this is kind of a summary of what we have achieved in our group in the last few years. And back in 2019, we demonstrated the first binomial code. And then 2020, we have this two logical qubit gate. I remember Luyan has a very nice paper on this entangling gate, maybe a couple of years ago, even earlier, right? In 2020, we developed this fault tolerant, the error transparent phase gate. In 23, we finally beat the break-even point of quantum error correction for the binomial code. And recently, we extended the error correction from one module, one logical qubit to two, and we can do error correction in parallel. We can protect their entanglement. So I will try to pick up a few major results to explain. So this is the device, schematic of the device. This is the protocol of the first binomial code. And here is the procedure is very simple. You just do the encoding from the ancillary qubit and to the harmonic oscillator. And then you repeatedly measure the parity of this code. And if you have you find a parity change, you know there's a photon loss error. And you can just do unitary operation to correct it. And here we use a two-layer correction that's tried to minimize the imperfection of the recovery operation itself. But here, this is the experimental result. And the green curve is the binomial code with quantum error correction. And compared to the red one without quantum error correction, we definitely have a big improvement. So this is the process fidelity of this whole thing and the function time. But this lifetime protected one is not beating the break-even point yet. That's the blue curve defined by the 0 and 1 state levels of this system. And it's only short by about 8%. Then the question is why we couldn't do we can surpass this break-even and how to do that. And it turned out the operation fidelity is not high enough. And in this experiment, the fidelity is about 97 to 98%. And in order to do this, we have to do some improvements. And one of the limitations is going to be the ancillary qubit. Or the ancillary qubit participates in both the error detection and error correction. And its role is very critical. And based on the simple error propagation model, and we find if we can just increase the lifetime, the T1 of the ancillary qubit from about 30 microseconds in our device to about 60 microseconds, and we can break the even point. Another approach is try to develop more sophisticated control techniques to improve the control capability. In the following year, we just came up with this error transparent gate. The basic idea is this: you have a Hamiltonian, you have a pulse to drive your system, and then the system, the quantum system or the code will evolve in the code space. But during the evolvement, during the evolution, if there's a sudden error happens, and then the code will jump from the code space to the error space and continue to evolve. If you can monitor, you can manage or engineer your system, the interaction, then the evolution in the code space will be identical to the one in the code space. And then after the gate operation, you can distinguish between these two spaces, and then you can recover. And in this case, even you have error during the gate operation, the gate is still successfully applied to the code. And that's the error transparent. And in this work, we basically developed two techniques. And the first one is the photon number resolved AC stock shift. So basically, you apply a continuous pump, which is detuned from the transition frequency of the qubit. And by this pump, based on the AC stock shift, we can continuously and precisely tune each Fock state, frequency of each Fock state. And at a certain drive frequency, you can get this error transparent condition. And this we call the pass technique. Based on this, we can greatly reduce the dephasing effect on this on the logical qubit, and therefore we can improve the control of the logical qubit by doing this technique. Another one is we develop this autonomous quantum error correction. So that's basically we do a unitary transformation, and again, this uniform transformation is realized by the graph. And we just transfer the error entropy. If there's any error associated with your logical qubit, you transfer this entropy to the entropy of this ancillary qubit. And then all you need to do is try to reset this ancillary to clean the entropy and for the next round of protection. And you can either do the measurement plus feedback to reset your qubit, or you do the dissipation through another very dissipative channel to get rid of this excitation of this ancillary. And for this kind of autonomous quantum error correction, since it does not require the error detection, it's just the unitary operation, whether you have error or not, I just do this operation all the time. So you don't need any fast feedback control. So this can avoid the latency in the control electronics that will be minimize the hardware requirement. And later on, I will show you we use this technique to also build the break-even point of binomial code. So based on the pass technique, as I said, use the pass, you can improve the control fidelity, and also with the significantly improve the coherence of the ancillary qubit. Now it's about 100 microseconds, and we finally can build the break-even point. And here, I guess the result is basically here we can surpass the break-even point by about 16%. And in a back-to-back publication, the Yale group also beat the break-even point based on the GKP code and in the same year. So recently, we just move on and from one quantum error correction to parallel quantum error correction, try to protect the entanglement between two logical qubits. And we know entanglement is a very important quantum resource and very important for quantum teleportation, computation, and also the metrology. And the idea is very simple, right? If you have two entangled physical qubits, whenever you have a decoherence on either one of the qubits, and you lose the entanglement. But if you have entangled logical qubits, and the coherence happens on either one of the logical qubits, that one will not destroy the entanglement completely. You just transfer the entanglement between the code space to code error space, or even error space. And then we can use the simultaneous quantum error correction to recover the entanglement between the logical qubit. So that's basically the strategy we are doing. And this is the device we are using. We have 3 cavities here, and we call S1, S2, 3. And we use S1 and S3 on our logical qubit to encode quantum information. And we have 4 ancillary qubits. And this is the schematic of this device. And we first generate the entanglement between the 2 physical qubits and wear this bus resonator. And then we just map the information from the ancillary qubit to the logical qubit. Then we can generate the entanglement between these 2. And then we turn on the simultaneous error correction on each logical qubit. And then we can protect the entanglement between them. And here I just show you the result. And we generate an entangled logical qubit, and we just measure the state fidelity as a function of time. And for the yellow curve, that's basically the lowest one. The fidelity will decay very quickly. Now, if you turn on the simultaneous error correction, we can bring up the green curve. And so that's improvement is about 45% in terms of the decay time. And based on this logical qubit, we can entangle them together and we can protect them. And we just do a Bell signal measurement, and we can see the violation of this, the violation of Bell signals, the Bell inequality. And here the green curve is with quantum error correction, and you can see a big improvement. And with even more purification, and we can see the Bell signal can surpass the classical bound here by 13 standard deviation. And I think this is the first, as far as we know, the first Bell inequality measurement based on logical qubits and also with quantum error correction. So this is a very recent work, and we try to do autonomous quantum error correction. For the previous one, we use the feedback, and we do error detection, we do feedback, and we can beat the break-even point. Here we use autonomous quantum error correction. The device is very similar to the one I just showed you for the entanglement protection. And we have 3 cavities. Here we just use 1 cavity to store the quantum information. Okay. And this ancillary qubit is only for the encoding and the decoding. And we first do the autonomous quantum error correction to transfer the error entropy associated with this storage cavity to this Y1 ancillary qubit. And then we need to reset this qubit. But rather than resetting this ancillary qubit directly, we swap this one to another ancillary qubit. And then we reset this qubit. The reason we are doing this is because the resetting in our experiment is kind of slow. It takes a few microseconds. That one will significantly deface this logical qubit because of the interaction between them. And by swapping this, we can do the swap in a relatively faster way. And we can swap the excitation from Y1 to Y2. And the resetting Y2 will not cause any dephasing because of the interaction is much weaker. And this is the experimental result. And actually, the second one from the top is the one with quantum error correction. The third one is the break-even point, the 0 and 1 coding. And we only overcome, the lifetime is only longer, few percent longer, actually, than the break-even point. But in any case, I think this work also very kind of a fundamental question raised by this paper. We can preserve quantum information for a longer time by only introducing additional drives and dissipation. Here we just, this reset, by the way, we don't have any feedback. For this reset, we just couple this ancillary qubit to a very low readout cavity to reset this ancillary qubit. There's no feedback control, just the drive plus dissipation, then we can preserve information for a longer time. So that's for the quantum error correction part. And let's go back to here. Since now we can build the break-even point of quantum error correction, and we have a single and multiple logical qubit gates, but there are still remaining challenges here, right? And we are facing basically two core challenges. The first one is still the question is how to further improve the quantum error correction to maximally protect the information. In other words, the depth of the circuit is still constrained by the imperfect quantum error correction. And the second one is how to scale up the quantum system. And basically the circuit width is limited by the number of logical qubits. And one solution is this the so-called distributed quantum computation. We can still based on the bosonic code. And on one hand, we need to improve the error correction performance. We said we can only hit the break-even point by less than 20%. And for the GKP, they can by a factor of 2. And I think, well, the question is whether we can do this by even more, by a factor of 10 or 100. That will be a next goal for us. And also we needed to expand the system. And inside of the node, we needed to add more nodes there. And also we need more nodes connected by quantum connections. So now we'll discuss about our effort towards this direction. And first we developed a new quantum state transfer scheme. So that's basically a device like this. We have 3 cavities, S1, 2, 3. This is within inside a node. This is one module, and we have 2 ancillary qubits. But we can turn on the 2-mode squeezing interaction between neighboring cavities. And by doing this, we can get a beam splitter interaction between the 2 remote cavities, S1 and S3. And during this process, there's no carrier exchange between the 2 carriers, between the 2 cavities. So this is just an analogy to quantum teleportation. You just use the entanglement as a resource to do this transfer. And this new quantum state transfer scheme, we think will be useful for the microwave optical frequency conversion and even the coherent conversion between telecommunication channels. So this is within one module, and we also try to physically separate the 2 modules. For example, we have 2 cavities. We can use a transmission line to connect the 2 modules to separate them physically. And here we use the so-called snail. This is a very nonlinear system, and as a coupler, this one can provide a strong beam splitter coupling with a very presumably high on-off ratio and more controllability. And I think we follow the work from the Yale group. And we know this beam splitter interaction is very important for this kind of high fidelity quantum state transfer and entanglement distribution. And we just made a device, and we have a aluminum superconducting cable connecting them together and put them in the same dilution fridge. And the transmission line turned out to be very good. Actually, we have the Q is over 1 million. The lifetime is about 70 microseconds. And we can have the two modules. We can have the beam splitter interaction on the order of megahertz. And based on the error analysis, we found this transmission line is not the limiting factor for the transfer of state. And here we can see continuous back and forth state transfer between the two modules. And then we can extract the number. This process fidelity is about 99%. The efficiency is close to 95%. And we can have remote entanglement. Fidelity is about 92%, 95%. Here I just show you the two modules. They are connected with the superconducting cable in the same dilution fridge. But in the future, we want to have even more connection with remote dilution fridges. You definitely need optical photons. So in that case, you need a microwave to optical conversion. So everybody wants to do this. But the optical photon and the microphoton, they have a huge energy gap. They don't interact directly. And the way we are doing is try to use the photon here. And the photon and around 10 gigahertz, and the photon can have a frequency match with the microwave. And they can interact with each other through the piezoelectric effect. And on the other hand, the photon has a wavelength match with the optical photon. And then we can use the photon as a medium, and then we can have a coherent conversion between the optical photon and the microwave photon. So first we have to make these photons there. And we call this the photon circuit here. So what we did, we have the sapphire substrate. And on top of that, we have a very thin layer of the piezoelectric materials. Here we use gallium nitride and lithium niobate, which is a few hundred nanometers thick. And then we do the lithography, we do the etching. So we only have a very narrow, the width is the order of a few microns wide. And we can have a ring, have a cavity, we can have a transmission line. You can have IDT here to introduce photons in this waveguide, in this transmission line. And you can also, we can measure the spectrum. Actually, here we did see the very dense mode of this cavity. The spacing is about 5 megahertz, and we have the Q in the order of few 10,000. It's not high enough, but it's good for us now. And based on these photons, and we can really see the microwave to optical conversion. So this is one of the package device. So the chip is like this. So we have this wire, so that's basically the photon here, and we have IDT. Again, we use the microwave. We use the IDT to convert the microwave to photon. The photon will propagate in this traveling waveguide from the left to the right. On the right-hand side, we have the input photon. It's optical photon. The photon travel from right to the left, and they travel in the same region, and they're going to interact with each other, and they will convert the output photon, propagate in this direction. And this is our experimental data, and we have the conversion efficiency. It's not too high. This is kind of the efficiency we quantify. That's the photon to the photon conversion. That's about 2%. And we have a lot of other loss here. From the microwave to the photon conversion, that's only the order of a few percent. But we think we can optimize this IDT by doing better impedance match. We can improve this quite a lot. We should be able to do that. And the things for this, this is a microwave, the gigahertz microwave, and to the optical at the telecom frequency. And it has very, since this is just a traveling wave, has a very large tunable bandwidth. The microwave can have like 300 megahertz. We can have optical frequency with 13 nanometer tunability. And this is on the solid state chip, and we think it should be more scalable. And based on this microwave to optical conversion, we can actually do the readout of the qubit. And so this is the general measurement, the wiring of the system. And we have this M2O microwave to optical conversion at the 4 Kelvin here. And So basically, this is our device, a superconducting qubit here, and at the base temperature, and the general or the conventional readout signal will be converted by this microwave to optical converter to optical frequencies. And we can measure, and then we can measure this optical signal at room temperature. And we can also use the similar things to control the qubit. So here we just, at room temperature, we can modulate the RF signal to the optical signal and can be injected into the fridge. But also at 4 Kelvin, we have a UTC. This is a uni-traveling carrier photodiode. And this one can demodulate the signal back to the radio frequency, to the microwave frequency. So this microwave frequency can control the qubit, can rotate the qubit. And in this way, we can have all kind of full optical control and readout of this system. And here I just show you the data. So basically, this is based on the optical to microwave conversion. We can control the qubit. So this is the Rabi oscillation, the rotation on the qubit. And here, based on the microwave to optical conversion, we can have simultaneous readout of the qubit. All these are experimental data, but since here we have to do a lot of average, and the efficiency is still not high enough. So that's, as I mentioned, the bosonic modes, and they are also good for other applications. And in general, conventional quantum metrology, and people try to use the large entangled Luyan state or GSD state to do the metrology. Another example is this LIGO, the gravitational detector, and gravitational wave detector. They use the squeezed state for better sensitivity. But all these large entangled Luyan state and GSD states, they are not easy to fabricate in the lab. And also we need this approach need the non-local operations and measurement. But bosonic modes can offer the advantages of the single mode quantum sensing. And again, this quantum system is just harmonic oscillator. It's a very clean system. It's very good. It can be very easily manipulated, and also with a very good dimension efficiency, right? Because its dimension is high. And we can use this single mode to do quantum sensing. And this is in 2019, and we use the 0 plus n as a probe to sense, do a phase estimation. And these are basically the Wiegand functions of 0 plus n, and you see the oscillation is very fast in this angular direction, and also this oscillation period is proportional to n. That means you do the phase sensitivity. Phase estimation, you should have a sensitivity proportional to n. And here, that's the experimental result at that time. And we indeed have the sensitivity approaching the Heisenberg limit. And at n equal 12, we have about 9 dB improvement over the classical, the Shannon noise limit. And this is based on 0 plus n, the superposition of this state. And in the following work, we use the 1 plus n state, because 0 and n states, this code has you cannot do error correction. Once you have a photon loss, you just lose this superposition. But if you have 1 plus n, if you just lose 1 photon, you can still do the error correction. Although this 1 and n, they do not satisfy the error correction condition, right? But we can do approximate quantum error correction to partially recover the information. And then we can use this superposition state in the cavity. We can really measure the microwave level in another cavity through the cross-current interaction. And we can do repeatedly for this approximate error correction, and we can try to improve this sensitivity. And again, I just show you the result here. We just need to use 3, 5, and 7, because all these states, they are odd numbers. So we can still perform the parity measurement to check the error. And here, Just plot the sensitivity as a function of the integration time. That's basically how long time for this sensor to interact with the device, with the microwave you want to detect. And here the black curve is basically the 0 plus 1 for that particular state. And that's just as a reference. And the blue is for different superposition state correction. And with error correction, you can significantly lower its sensitivity. Here for the 7, I think it's similar. In the end, we get about 5 dB improvement by doing this single mode and plus the approximate quantum error correction for the radiometry. And there's also the other works, for example, and this is last year from the Southern University of Science and Technology. And actually, my graduated students, his group, tried to use Fock state with the metrology, try to measure the displacement and phase. And they found at Fock number 40, we have about 15 dB improvement. Here also and they use 0 plus alpha cat state, and they can also do the metrology. It's approaching the Heisenberg limit, and at M bar, actually is relatively not large M bar. You don't need a very large M bar, and you already have over 7 dB improvement for the sensitivity. So I think I'm going to just summarize my talk. And I think for the bosonic code and bosonic mode, the shorter term, we need to explore their applications in quantum repeaters, simulation, and metrology. More works on the metrology. There's something I don't have enough time to talk about this, but our group, we are thinking to use high Fock number state to do metrology. When I say high, I mean hundreds of photons, maybe even 1,000 photons. You should be able to have a very large metrology gain by doing that. Another direction is quantum machine learning. I think now the machine learning the AI is very popular. And I think combine this bosonic system with the machine learning, I think we can have some I don't know, have immediate applications, but we can have some proof of concept demonstration. So this is some related work we did. And for the long term, it definitely for quantum computing. And we need to keep improving the coherence of the system over the ancillary qubit and the cavity. And we need more advanced quantum control techniques to realize more fault-tolerant operations. Again, for the scaling is a very big challenge. For higher order code, you can try, and for phonons, and another for the cat qubit. I think that's one of the things we are trying in our lab. Again, for the distributed network, that's the things we are working on right now. I think that's pretty much all I have to say. And finally, I want to acknowledge my collaborators, especially Changlin Zhou from USTC, who provides a lot of theoretical support for our quantum error correction work. And also, we have a close experimental collaboration on the phonons, on the microwave to optical control, and all others here. And also, I thank my graduate students and the funding agency. With that, thank you very much.